Hello, I'm Rich Eisenberg, the editor of Inorganic Chemistry. As part of our 50th anniversary celebration, we are having a number of interviews with leaders in the field. Today's guest is Professor Tom Meyer from the University of North Carolina, Chapel Hill. Tom is a leader in electron transfer chemistry, transition metal photochemistry, catalysis, solar energy conversion, artificial photosynthesis. It's a great pleasure to have Tom here. Welcome. Tom has been an award winner of the ACS Award in Inorganic Chemistry and Distinguished Service Award for the Advancement of Inorganic Chemistry. He's a member of the National Academy of Sciences and a leading light, as I've mentioned before. So, Tom, let's begin.
That's very impressive, Rich. I like that. Good start. Sorry.
Let's begin with tell our listeners and viewers about the early years. How did you get into chemistry, and what moved you forward?
Well, this is assuming being a chemist is moving forward in retrospect. No, you know, it's an interesting story, because I think you may recall there was a time when there was a thing called Sputnik, and the nation decided that it really had to do something about its science and technology. And I got trapped and snared in that move. There were some really interesting programs for kids. And I still remember this. I had this wonderful high school chemistry teacher who was what he was in part because there was special funding and they attracted him, and he did a great job. So he convinced me there was something in chemistry that was of value. I then went on to university, and you know the way kids are, without thinking about it, I had to sign up for courses, and so I signed up for chemistry. And then the second fatal blow, I had a really spectacular first-year freshman chemistry teacher, a guy named Bob Klein. The high school teacher, by the way, was John Bisbocci, and he's still around. He's still doing his job. And this guy Klein sort of took me by the scruff of the neck and made sure I took chemistry courses. I still remember at the end of my undergraduate experience saying, well, I got to go to law school and do something interesting. I never got around to doing that. I ended up going to Stanford to graduate school, and as they say, the rest is history. So in a way, I think you know, the fact that I'm a chemist is almost not an accident, but really was the product of some really superior instruction and some really good teachers. Made a big difference.
When you arrived at Stanford, you worked for Henry Taube, one of the giants in our field.
Sure was.
And tell us a little bit about that.
Well, Henry was this Canadian, relatively small in stature, very distinctive and idiosyncratic personality in many ways. As a scientist, and those who knew him knew this, he had literally a brilliant intellect, but extraordinarily creative. People really responded well to him. I think he was relatively self-effacing. You know, ours is a funny business. In order to succeed and make up brand new things, you've got to have a lot of confidence in yourself. And if you don't have a big enough ego, you simply can't survive. It's just in the nature of what we do. And the thing about Henry that was, I think, really impressed people without them knowing it was he was so offhanded about it. You never heard Henry in a very aggressive way talk about himself. I knew him very well, though, and discovered he was the ultimate egotist because he had perfect self-confidence in himself. He didn't have to carry his life on his sleeve. So in addition, I think, to being this remarkable scientist, he had a winning personality, and people really responded very well to him.
Now that drew you into electron transfer chemistry.
Sure did.
Photochemistry. Yep. And the other threads that served to set you on the course at North Carolina. Did you do postdoctoral work?
Yeah, but go back a step. I mean, the thing I learned at Henry's knee was electron transfer chemistry. At that point, if you look at the history of our discipline, he and the group at Northwestern, Fred Basolo and Ralph Pearson, had really done master work in introducing the basic concepts of mechanism and how chemical reactions occur. And Henry was really in the middle of that, and his work was really outstanding. At that point, the thing that he was doing, well, that he won a Nobel Prize for in the end, was electron transfer, the demonstration of mechanism. That was really the key. So that's really what I learned from Henry. I remember still I was a second-year graduate student, and I decided I wanted to go to Europe. I figured that was a smart thing to do, and so I decided I would apply for a NATO postdoctoral fellowship. And I still remember I'd been a graduate student for a little over 2 years, going to see this guy who's a future Nobel laureate and saying basically, Henry, you know, I've been here for 2 years. I've learned everything I can learn in your group. Can you give me some advice on who to go postdoc for? And he was so gracious about this. If it were me, I would have killed this student. You know, I probably would have. And he recommended, he said, well, there are only 2 choices if you want to go to London, and I did. Wilkinson and this guy named Nyholm. And he opted for Nyholm because Ron was a physical inorganic chemist of great distinction. He was an Australian guy. And at that point, he was really riding high in British science. And so I went and postdoc for him.
And then from there you went to?
The UNC, that's right.
Right. Do you remember the initial experiments that, let's say, led to your eureka moments, your aha moments, where suddenly things worked out and you said, I think I have this field cracked, or at least part of it?
I always tried strong drink. That often triggered the appropriate response. No, I think looking back at some of the things that, that are associated with my name, there were some important moments. And if you fast forward, well, one of them was just the whole notion of picking up this polypyridyl ruthenium and osmium synthetic chemistry. Mm-hmm. There was a guy named Dwyer in Australia who in the 50s and 60s, with some spectacular associates like David Buckingham and Alan Sargison, sort of invented this whole area of coordination chemistry, and people hadn't paid any attention to it. They dropped it. And I was wise enough as a graduate student and as a young faculty person to go back and look at that. And what I wanted from the very beginning was to look at problems in chemical reactivity. And it was a very special part of the periodic table simply because of the stability associated with complexes of ruthenium and osmium. So what that meant is you could, if you did the synthetic chemistry right, you could build a complex, and then you could leave parts of it left over to study chemical reactivity and focus on that. So I think the first thing was just getting the world back into this and discovering some really interesting reactivity, I think, that had an impact in bringing people's attention to the area. That's one thing that occurs. I think in terms of not so much eureka moments, though, but one certainly that comes to mind was these experiments that we did very early with a guy named David Witten, who's a friend of yours, physical organic chemist. We're still very close. He used to be on the faculty at UNC, and I was the electron transfer guy, and he was the organic photochemist. And at that point, believe it or not, organic chemists didn't like to think about single electron transfer. They simply refused to accept that it could happen. And it occurred to me this was pretty straightforward. And we were doing this ruthenium chemistry, and Dave had just built a flash photolysis apparatus. So I remember my saying to Dave, or him saying to me, although I'm sure it was me saying to Dave, hey Dave, I got an experiment, let's try. He provided the methyl viologen, that's this methylated pyridine thing, it's an electron acceptor. And I had the rubipi, and we put them together with a graduate student named Randy Bach. Did a flash experiment where you flash the solution, you look at what happens, and bingo. If you look, there was a strongly reduced methyl viologen thing. And in the beginning, it was just a proof of concept. It was a paper in JACS. But boy, after a while, if you stare at what had happened, there was something very special because, as you well know, what we did with the light that got absorbed to make the excited state was to then pass it off to this methyl viologen, leaving behind a ruthenium-3 complex that was strong enough thermodynamically to oxidize water to oxygen, and the methyl viologen was strong enough reductively to reduce protons or water to hydrogen. Mm-hmm. And so, bingo, all of a sudden, and this really occurred shortly after we did that experiment, this was a big deal, or could be.
That's right. And let me emphasize to the viewers that prior to that time, the notion of electron transfer quenching was really not very much established, in that work with the ruthenium complexes had been done on triplet sensitization,
yes,
energy transfer, but not on electron transfer. So that was really a seminal moment, I think, that moved your science forward.
Yeah, to put that just a moment, just to pick that up. Arthur Adamson was a very famous photochemist, and he had really pioneered using these complexes in that way for sensitization, but not for electron transfer.
Another area, again, which builds off of that or accomplishment was the energy gap law and the application to it, and then all the subsequent chemistry that has been in the realm of photochemistry for solar energy conversion. Tell us a little bit about your efforts over the last decade or so with regard to that.
Well, again, if I go back and look, it's really quite striking that initial observation with Witten, where all of a sudden there was an eureka moment where we discovered the basis is here to do conversion into high energy chemicals. So stop and think. So what do you do next? Well, one thing, that's fine, but they just come back together and undergo back electron transfer and make heat again, like everything else. So you needed to make advances in multiple areas to solve the problem. So what do you have to make the multiple advances in? Well, one thing, you pay attention to the excited states, and you don't want to do diffusion. You first understand the excited state, do the synthetic chemistry to put the pieces together to make everything faster, molecular assembly. You then have to learn about the photophysics because you really want to learn about, well, how long does this excited state last? How much time do I have to use it? What are its energetics? What can I do with it? So that led to this quantitative study that I still think was spectacular. If you look at the area of photophysics today, organic versus inorganic, we know so much that have come out of this polypyridal photophysics. The molecules themselves helped a lot, but we really have learned immense amounts. Anyway, that was an offshoot, those first experiments with Witten, as were things like water oxidation, because we had to figure out how to do that. Nobody had figured that out, so we had to go off and worry about water oxidation too.
The notion of application in research today is very, very strong. And I'm going to ask you to actually give some advice to young inorganic chemists starting out their careers, because at the very beginning you were doing very fundamental science, very dealing just with electron transfer. And it suddenly became very, very critical for artificial photosynthesis and solar energy conversion. Now we seem to have a lot which is going on with regard to what good is the research you're going to do rather than how fundamental or how important does it contribute. Give some comments, please, to our audience with regard to that, advice to young people starting out.
Well, I guess I don't have mixed feelings, but if you stop and think about why it is we do what we do and why your fellow taxpayers and citizens contribute through their taxes to keep your research lab going, there are certain expectations. Inside that, though, the facts of the matter are that when we move forward, if it's guided, as it often is, by an ultimate end, you can only go as far as your knowledge base begins. So let's think about this. My observations about this always were that, sure, we were doing fundamental science, but in part, in the back of my mind, was the fact that there was a reason to do that. Electron transfer was studied in great detail. We'd had theoretical advances by Marcus and Hush, and Henry had done terrific work. The next step was, if you start, for example, going back to this driving light of artificial photosynthesis, you still got to solve the problem of electron transfer, so you better think about that and build it back into these assemblies, and then discover about electron transfer in them. So I always found it enriching to be able to think ahead, often when we did these things. Now, having said it, there are diversions where we really do need to take the time to unravel things. I would argue that to chemists, that one of the triumphs, of the 20th century in chemical sciences was the deep understanding of electron transfer. Although we don't teach it to our students very well, we really know a whole lot and we can count on it. That did not come easy, but because it's there, we really take great advantage. So I think what I would argue is, you got to be careful about it. If you're collecting a lot of information just to collect it without any end whatsoever, it may be wasted time. On the other hand, and therefore if you can, keep the work that you're doing in mind with a larger perspective it adds value to it and to you, and that's great. The real danger, though, and we've done this to ourselves, is people get so passionate about actually doing something useful with their work. And so people leap ahead and try to make great advances. And it just doesn't work that way. Very few people are that lucky. And so we really need to remind ourselves as scientists, and certainly those who provide us with resources, that to get from point A to Z, there are a lot of stops in between, and you better make them, right? And so there's this balance. Fundamentals, understand there's a reason to do them, and you are not going to get to the end until you fill in the blanks. And we need to remind ourselves of this as a scientific community.
Let me follow up on that with regard to what you're currently working on. You mentioned it briefly, which is water oxidation. And making oxygen from water using sunlight is an essential part of any artificial photosynthetic system that will be on a large scale. But let's take a look at and describe some of the real interesting challenges associated with that. It sounds simple enough. 2 oxygens, strip off 4 protons, strip off a couple of 4 electrons, and you've got, poof, oxygen.
Poof?
Yes. It's not that way.
No. Well, look, remember, though, go back to my point, the water oxidation story goes back, way back. That's part of a larger picture that I'll come back to later. You have to solve that problem and then plug it in with a larger assembly, something, a components approach. But anyway, go to water oxidation. So what happens historically? I described the experiment with Witten. We got this strong oxidant solution. If you wait for it to oxidize water in acid solution, the half-time is centuries. It simply can't, because all it can do is make a hydroxy radical. It's way uphill. So you got to do something. So very early on, I had this graduate student, Bruce Meyer, who said, well, boss, we should put water in the coordination sphere. So we did. We took a BIPI out, put water in, and started to look at the consequences of that. You oxidize that, and it turns out then you get a stepwise oxidation to the next oxidation, state 3, and pass that to 4 because you make an oxo. And the oxo, the protons are stripped off, the oxidation state stabilized, and that was terrific. And I still remember Brucey doing this. So he puts this aqua complex in solution, he puts in cerium, he stands and looks at his beaker, he's waiting for oxygen to come out. It never came out. This was 35 years ago. The problem, of course, was thermodynamically it wasn't strong enough. He was off by 1/10 of a volt. He actually had the problem solved 35 years ago, but we didn't discover that until 2 years ago. It took 35 years later for us to actually dig this out. We did, though, go past that and decide that we needed to look at other generations of molecules, and sort of took one and put an oxygen bridge between 2 with the same structure, and discovered it did do water oxidation catalysis. But the best ones we found, catalysis-wise, actually and ironically, are very much based on Meyer's original idea, and we just discovered this 2 years ago. After a hiatus on my part, we went off and did other things besides chemistry.
Now, you've run a fairly large group over the years. What advice would you have for younger scientists trying to run and manage a large group? It takes a particular talent and skill.
Well, it sure does, and I don't even worry about that too much. I mean, I'm very conscious of what it means to manage and deal with people. But in my experience, nobody succeeds in this business unless they're pretty good at it. That is, creating a large research group. You have to be able to do what? You have to be able to get along with people at some level. You have to be able to manage, because there's money flow, everything's a complicating feature for multiple grants, et cetera. And my observation has been that people who do well have those kind of talents built in. But what I would say to young people who want to enter this fray, I mean, you really do have to be conscious of the fact. You have to be patient. You really do have to be patient. You've got to remember, this is advice that transcends just research. Just remember, everybody's a potential asset. You just have to figure out a way to get it out of them. This is looking at it from the educator, sort of research scholar. And then again, you have to have a certain modicum of organization, or you really shouldn't be in this racket, because you do have to be able to, how should I say this, tie your shoes and eat breakfast or read the newspaper at the same time. And so there's certain innate skills you better have, or you're not going to make it.
Do you want to talk a little bit more about the the challenges that are facing chemistry with regard to sustainable energy?
Sure, let's do that. There's an historical element of this that's absolutely ironic in the following sense. So I was trained as a graduate student many, many years ago by this guy, Henry Taube. And I remember when I was in his group, one of the real challenges was doing things like take oxygen out of the air that's everywhere and is this strongly oxidizing chemical and do something useful with it. And that's one of the projects I worked on. I go to meetings here and people are still trying to figure out how to do this 40 years later. What happened? You know, in other areas of science, you know, the physicists build big machines, we do calculations, people just carry out reactions and make all these wonderful structures. The problems at the heart and soul of renewable energy, the way we think about it, where some of the keys are making conversions, for example, of water to hydrogen and oxygen for fuels, if you really want to do that, these are very difficult problems. They come slowly. It's been very hard for people in our business to maintain sustained research efforts. This is the kind of problem that national labs work on over an extended period. But a lot of this work almost has to be done by individuals taking chances in different ways. We haven't had the research support to allow people to do this. The physical sciences and support for them in this country through the National Science Foundation and basic energy sciences at DOE, their budgets have fallen over a period of 30 or 40 years. The NIH budget's gone up by a factor of 3. And now we find ourselves in the position deciding, oh, wait a minute, we better do something about this. You know, I gave this talk on Monday that said, you like solar energy? If you don't find a way to store solar energy, and the only way to do that is in chemical bonds, forget about it. It will never be a primary energy source, ever. Throw away your silicon solar cells. I don't care. It's chemistry in the end, and we still don't know anything. So I understand how this happened and why it happened. The problems are very difficult, as you're well aware. You're in the middle of this. We haven't had adequate support. The funding mechanisms have never been there for sustained hard efforts. It's not the kind of thing the national labs have done. Industry was smart enough to walk away years ago because it was so hard, and now we're in a pickle. We really have to address some of these issues and try to resolve them in a relatively short period of time. I think it's very encouraging, in fact, that at the tail end of the last administration, the Bush administration, the Department of Energy came up with these so-called Energy Frontier Research Centers to address some of these issues in this broad array of problems that the DOE faces, that the world faces. And now there's this new program, the so-called Energy Innovation Hubs, which is the same concept in a way but on steroids, 10 times bigger. These are all kind of experiments. They will all work at one level or another. The country and the world need to make a huge jump start, and this is a down payment. Even at that level, the amounts of monies we're talking about investing are just the beginnings of what will be required to pull this off. So I think, you know, there we are, in pure irony, people like us who were trained this way, who make a living doing this way, are starting to disappear. The younger generation doesn't exist. You know, there's never been a popular area, difficult to do, and it's a real dilemma for us. We have to rebuild a community here somehow.
I think one of the important problems when you talk with students today and your postdoctoral mentees about projects to work on, that solar energy and alternative energy represents the most compelling challenge that doesn't deal directly with human health, but is the most compelling challenge in science today outside of that sphere, outside of the health-related science. And I hope that we can continue to have the sustained effort that you talked about to address that.
Well, hopefully this time around, there's been enough free publicity by various issues related to energy and the environment and the general public that we will have a sustained effort. It's been interesting to watch the general public reaction to this apparent problem. What is this energy issue? There has to be one. What are these guys talking about environmental issues? And there is, as usual, a disengagement between them and the experts. In my position as Associate Director at Los Alamos, for example, I had 3,000 employees and a budget of $610 million, and discovered inside that one of my portfolio areas was energy and the environment. And so I collected these guys, and they started to teach me things I didn't know about. And all of a sudden, I got very nervous when I looked at what they were telling me. And why was that? Because if you look at what our growth is, for example, if you look at the growth of the global economy, and you make connections, it's powered, as our economy has been for the last 100 years, by inexpensive energy. There's a direct correlation between quality of life. Well, and if you look, China, India, East Asia, Indonesia, their economies are growing rapidly based on energy. But where is it going to come from? We're probably approaching the peak of oil production. Look at the environmental problems we're facing. Maybe a little controversy in the papers, not amongst the experts. There is increasing evidence that temperatures really are rising. Is that important? Is that of major consequence? Well, there are those who say, well, enjoy it. It'll just be hotter. But then somebody else points out, if the temperature goes up 4 degrees by the end of the century, 4 or 5 degrees, and it could go up much more than that, it's conservative, all of a sudden look at the Arctic. It is beginning to melt. Oceans are rising. By extrapolation, by 2100, the ocean rise will be at least 4 feet. The average altitude of the Outer Banks of North Carolina is 3 feet. Most of Florida, the beaches are gone. What are you going to do about New York City and Boston? What's 4 feet mean to them? This is for real, right? If you don't intercept and do something about it. So I give this general public lecture, and I've discovered I have to be very careful, because if you're too negative, people actually get depressed. It's nice to watch the students respond, though, because they do. You look at them and say, it's your problem. And now we have to give them the wherewithal, I think, to pitch in. And the only thing I think that concerns me is I began, forcibly picking up on these issues, say, about 10 years ago. And boy, there was a long period when nothing much happened. And we're running out of time really quickly. We have to move.
How will research change? You mentioned before about your time at Los Alamos, and bringing different people, engineers, physicists, chemists, together to talk about their common interest. How do you think chemical research will change in the future? We do discuss more multidisciplinary, interdisciplinary work. And how will it stay the same from what we have done during our careers?
Well, I'm convinced we need a new way of doing business broadly across science to address the problems that I just described at a very high level. Let me start with that, then I'll come back to chemistry. Because really, you need to find what we try to say is a combination between the way our national laboratories operate and the best of academic science. The national labs have stability, they identify important problems, and they stay on them for a long time. They have permanent staff in place, they have instrumentation as needed. They are not flexible and nimble, as you know. Academics, they're a wonderful bunch of occasional airheads. They are brilliant, they make things up, but they simply can't stay on a project more than X years, where X is not big. In fact, the National Science Foundation, if you do something for more than 6 years, will automatically take your money away. And so we're caught in a real trap here. What we need to do is to blend them together in a new way of doing business. And first, just think about the mechanics of that. What does that entail? You need to have sort of permanent staff and instrumentation in place that people can count on, so they don't have to spend all their time doing that. Every time a good student leaves, you have to start over again. You don't have time to start over anything. So with the permanent staff in place, the students become an afterthought, except I've done this. This is a spectacular environment for them. They get things done, they watch, they see how things work. But we really do need to put this together a brand new way. And there is no good model. The Max Plancks in Germany have some of the features, but that's not right. We have to start this over. And that's why these EFRCs and hubs are so important if we do them right. Now, where does chemistry fit in? Well, chemistry is a very funny discipline. Parts of physics are this way as well, in the sense that a lot of this depends on bright, clever people making things up as individuals. They look at a chemical problem and they use their nuances. To an extent, you might be able to build that into a hard-charging organization where you're going across doing things systematically. But I think there'll always be a place and an element for people inventing brand new things in our business. But what you need to do then is find some way to support that effort and on demand bring them into the fray as collaborators, give them a chance to enrich their lives and do things more broadly. You know, we see that in our Energy Frontier Research Center. I sure saw it at Los Alamos. All of a sudden, you know, with all these people in the fray, a week and a half ago I had this great idea about how to revolutionize organic photovoltaics, brand new idea. Well, I used to still have a fairly big group. I had 30 people in my group. It still would have taken me 3 years to do it because they're a bunch of brand new things. This young assistant professor down the hall can make me the bucketball of derivatives I need. You know, I've got my stuff and I can get measurements over there and all of a sudden we can actually do that, hopefully in a month. That's where you got to get. But remember, you need these bright, clever people doing their thing who will come together, who can come together to really address all this. And chemistry will be the middle of that, I think.
Will there be a different way of evaluating how well these young people are doing if they are working as part of larger projects, as opposed to having their own laboratory with a certifiably identifiable project with them? This is our cross to bear. I mean, what Richie's alluding to is look at our tenure system. So we go out and we hire somebody and as an assistant professor and we say, well, come and join us as a colleague. You've got probably 4 or 5 years if you're lucky. And if it looks like you might win a Nobel Prize, we might give you tenure, you know. And by the way, don't talk to anybody. Just get it done so we can prove you on your own merits. I think, you know, that leads to certain kinds of behavior. The people who survive tend to be rapacious and aggressive and get a lot done, and that's very admirable. I don't think it's very realistic now because just the nature of what we do. And what that means is that we, the seniors in the business, have got to be much more realistic about assessing. It's not that easy. And so it's up to us to figure out other ways to get the kind of input we need to make sure that these colleagues will succeed. I'm going to turn attention now to Inorganic Chemistry, our journal. You started your career just shortly after the journal published. You've been a regular supporter and a member of the editorial advisory board. Tell us a little bit about your perceptions of inorganic chemistry at the early stages of your career, middle, and now. How do you see the journal as a central place for your science?
Well, given what I do, I mean, I'm actually sort of cross-disciplinary in the sense that I'm half physical chemist, probably to be truthful. But you know, I came from, and my home still is inorganic chemistry, and that journal represents, you know, what I do. It is the place for this important part of science to present itself relatively broadly, and your journal does that very well. In addition to provide, you know, ways to look at that audience and help them cross over more broadly. And I think the journal's done a great job. I mean, the leadership started with Fred Hawthorne, an old friend, very powerful intellect. You've done brilliantly in his place. I think the leadership has been terrific. I think the journal is healthy. It's wealthy and wise. So you guys should feel really good about what you've done. I think it's a great success.
What advice would you have, again, for younger scientists in terms of the importance of publishing in inorganic chemistry as a forum for their work versus publishing in other journals that may be sort of facing outward to different audiences?
You know, I think the answer is straightforward in that we train students in a certain discipline. They take courses in this discipline we call inorganic chemistry. They come out of that and they have, it's an affinity group at some level in some way. The world's a big, complicated place. Humans bring themselves together and wrap themselves around finite things to deal with. Having a core of information and people who, in fact, see each other at meetings is a very critical element of what we do. Inorganic chemistry is right in the middle of that, you know, for our discipline. So in that sense, I mean, you want that, but you also want to say to people, hey, look, it's really terrific when you take what this community has offered and you transcend and go beyond. You know, those people, for example, who start out in our business who end up doing an awful lot of bioinorganic chemistry and then biology, that's fine. And we should be proud of that. And we should expect that because people need to follow their nose. But in the end, they came from a place, and that place needs to be there for, you know, future generations. The whole notion of discipline means something in almost any human endeavor.
What do you see as the major challenges with regard to scientific communication going forward? The situation is very different today in how we disseminate knowledge. The situation is very different today than it was 15 years ago, even 12 years ago when journals started going on the web.
Mm-hmm.
How our students access information today, completely different.
Mm-hmm.
And how do you see that as a major challenge going forward for practitioners in the trade?
You probably need to talk to the teenagers like my granddaughter who's off text messaging her 3 boyfriends, right? I'm serious. We have to be careful about trying to answer this question, I'll put it that way. But there are certain things I have seen. For example, I can no longer write. I can only read and do PDFs. You know, I no longer write anything down. I think if you look at the way we communicate and what we do and how we do it, there will be, we're in the midst of and not completed of a revolution of sorts. Paper doesn't mean anything to, I think, to almost anybody except real old fogies. Therefore, that's a done deal. The whole notion of communication, though, there are other aspects of this. One, the journal part, I'm not sure what is out there in a revolutionary way to help inform us, but I suspect there almost have to be powerful techniques around the corner for providing information, you know, whether it be 3D imagery that will just, you know, change things, whatever. But there are other parts of this story we have to be really careful about, and that is, so what's the purpose of all this? Well, we inform ourselves. We instruct others about the physical universe and allows them to make progress. That includes the training of students. And let's go back and think about that a little bit in this context. I think, you know, there's a real dilemma there that we as educators better work our way through, and I don't see any innovation at all, but I'm sure I've missed it in the following sense. We still train graduate students by giving them 3 courses a semester. You know, the world is this hugely diverse place. It comes in slices. It doesn't come in, you know, big pieces anymore. Somebody should take the time to reinvent a graduate curriculum, for example. It's basically a whole string of special topics courses. The fundamentals need to be laid out at the undergraduate level. There are certain things you cannot escape. But past that, we better innovate and revolutionize because there's so much information to share. And I don't think we're doing a very good job at all. I'm very sensitized to that. And I'm also sensitized to the consequences of this exploding knowledge base. Because, you know, give an example. We were trained, I mentioned Basolo, Pearson, Taube, how to do chemical reactions, focus on chemical reactions was important. Every graduate student had information about this. Some ended up making their living doing it. Very hard to do, not fashionable, people forgotten. You know, most of that generation are gone. All of a sudden, we want to face up to renewable energy and this emphasis on chemistry. And I watch as people try to enter this area and don't know anything. They know how to do structures. You know, they know how to do NMRs. They don't have a clue how to do a mechanistic study. And they are, because of that, really inhibited in how they can progress and how they do it. And so we have to be very conscious, I think, of this shifting pattern of knowledge. We have to be very careful, I think, about how we deal with this. And I think this whole notion of redoing a graduate curriculum, in addition to then somebody writing materials for that. You know, I'm very conscious. If I do not, you know, before I give up the ghost, which may be sooner rather than later at this stage, of writing down what I know about things like electron transfer and all this I know all this stuff in a totally coherent way, and very few people, if anybody in the world, knows it the way I do. I lived it, you know, from graduate student to now, and I made up part of it. We need to benefit our colleagues and say to them, you really need to do this, and here's why. You know, here's a check for $50,000 from us out of gratitude, so we can train the next generation of graduate students, or some way to incentivize it.
I'll just give you an invitation to write that in Inorganic Chemistry, and in fact...
Where's the $50,000, Richie?
Well, maybe it'll be a little less. But I will recommend to all of you to read several papers that Tom wrote that appeared in Inorganic Chemistry forums an absolutely spectacular paper on this question of water oxidation and oxygen evolution, and another wonderful paper with regard to the reductive side of water splitting. So we've been talking today with Professor Tom Meyer from Chapel Hill, and have enjoyed sharing and hearing his particular views on a number of points in his career. And I want to thank you very much for coming and wish you good success in the problems ahead with regard to alternative energy.
Thanks, Rich.
We'll look forward to it in the future.
Good. Thanks for doing this.
Thank you.